Hello, friend. Jim here with Science Talk. I thought I'd do a bit of a different type of story. A little break from the always unpleasant climate news, and has to deal with the Earth's core. Turbulent blobs in Earth's core may explain sudden jerks in the magnetic field. Okay, so this is a little bit of some geoscience here. The Earth, as we know, the Earth has a magnetic shield, and it protects our planet from the blast of the solar wind, cosmic rays. I mean, the solar wind comes in, and the magnetic field with the magnetic field lines helps direct the solar particles and the field, where the particles follow the field lines. And if you live at high latitudes, you are usually treated to wonderful displays of the aurora borealis or the aurora australis, southern lights, and they're quite spectacular. After 30 plus years here in Alaska, I never tire of looking at them. And so they're given the cute title of geomagnetic jerks, and they're what basically defined as abrupt changes in the strength of Earth's magnetic field. Now, will there be some variations in the field? Sure, that's expected because it's a fluctuating fluid, literally and figuratively, a system. Right? The Earth's core is presumed to have a solid inner core, but a liquid outer core of nickel iron, and it sets up a electromagnetic field by the currents inside the core, and so forth. So, the fluctuations are expected to occur gradually over hundreds to thousands of years, but the sudden, as they call them, wobbles in intensity last at most just a few years. So very short-lived. And may only alter Earth's magnetism over specified parts of the world. So it may only affect certain field lines, not all the magnetic field lines. I think of the Earth as a big bar magnet, right, North and South Pole, with the field lines over it. And you probably remember doing that experiment in like grade school, something like that. You took a magnet and you sprinkle some iron filings, and then you watch how the iron filings coalesce into discrete, roots and lines and curves. One of the first jerks documented, as an example, briefly warped the field over Western Europe in 1969. Since then, a new jerk has been detected somewhere in the world every 10 years or so, plus or minus. Scientists, geophysicists are still not sure why they happen, what the cause is. And, many geomagnetic phenomena, including the auroras, result from electrified solar wind interacting with the Earth's magnetic field lines. The jerks are thought to originate from deep inside the planet's core, where the magnetic field itself is generated by the constant motion of the liquid iron. What's the mechanism? Unknown. So a new study published in the journal Nature Geoscience presents a potential explanation, potential hypothesis. According to a new computer model of the core's physical behavior, geomagnetic jerks may be generated by buoyant blobs of molten matter released from deep inside the core. So think of like a big lava lamp, right? What happens, right? We've all seen a lava lamp every so often, right? Big blob, and it goes up to the surface. Well, that's the analogy I want to use here to help get that concept across. So what was done in this study? The researchers built a computer model that very carefully recreated the physical conditions of Earth's outer core. The inner core is thought to be solid. So therefore, if it's solid, it's not going to be churning as much. And shows its evolution over several decades. After the equivalent of 4 million hours of calculations. Now, of course, the people didn't do this. A wonderful French supercomputer cranked this out for us. The core simulation was able to generate geomagnetic jerks that closely aligned with actual jerks observed over the last few decades. These simulated jerks basically, tweaked the magnetosphere every 6 to 12 years, in the model. However, the events seem to originate from buoyant anomalies that formed in the planet's core 25 years earlier. So apparently there is a lag effect, which makes sense. By the time the blob releases and then affecting the magnetic field lines, it has to travel a distance. That makes sense. That is not an unreasonable finding. As those blobs of molten matter approach the outer surface of the core, powerful waves were generated that then moved along the magnetic field lines near the core, creating the noticeable changes in the flow of liquid that governs the planet's magnetosphere. That's according to the authors. Eventually, these sudden changes translate into jerky disturbances in the magnetic field high above the planet. Jerks represent a major obstacle to the prediction of geomagnetic field behavior for years to decades ahead. Basically throwing a bit of a wrench in the system. Okay, so the authors go on to say the ability to numerically reproduce jerks offers a new way to probe the physical properties of Earth's deep interior / core. Now, as I've explained to you guys before in the past, when scientists develop computer models, it's not just make up some shit and then do it. Oh, let's see what the hell. Let's just do this, create this, and see what the hell happens. No, what we do is we've got our data. We've probably got differential equations derived from the data, which we then develop the functions from the differential equations, finding the solutions. And we program the computer, entering the equations, entering the data, and we run the models. And the first step is to get the models to reproduce what has already been observed. Once the models get to that point, when we do so with, say, 95%, 99% confidence, meaning that we're correct 95 times, 99 times out of 100, then we say, okay, the model is decent. Now we can extrapolate. So when people say, "Well, scientists, model it doesn't mean shit. You're just making stuff up." No, they're wrong, and you can tell them that they're wrong. You can tell them why they're wrong. So that's kind of what's going on, and it's why the term jerk. It's not in the colloquial as in English, not like, well, you're an idiot. Jerk is a specific term. Let me give you this explanation. You have a position function. Position function tells you where a particle is at. Okay? Usually is S is equal to, V sub 0 t plus 1/2 at squared plus S sub 0. Okay, V sub 0 is the initial velocity, t represents time, 1/2 at squared, a is acceleration due to gravity, and then S sub 0 is the initial position. That's a typical function in Newtonian physics. You can have other position functions that involve a higher order polynomial, like a cubic term in there, what have you. So when you have a position function, let's assume a generic position function. If you take the first derivative, ds dt, the rate of change in position with respect to the rate of change in time, that's called velocity. Right? So The instantaneous velocity will tell you what's the velocity of the particle at a specified point in time. If you take the second derivative, dv dt, the rate of change in velocity with respect to the rate of change in time, you get acceleration. Acceleration is change in velocity. So velocity is a change in position. Acceleration is a change in velocity. Acceleration also happens to be the second derivative of the position function. So you have the first derivative of the position function gives you velocity. The second derivative of the position function gives you acceleration, or the first derivative of the velocity function gives you acceleration. The jerk is dA dt, the rate of change in acceleration with respect to the rate of change in time. In other words, the jerk is a change in acceleration. So that would be the second velocity derivative or the third position derivative. So when you have the best way to think of this is go back to the Apollo program, the Saturn V, right? Liftoff, right? The big monster rocket is trying to gain altitude, all that thrust, and it's eventually gets up there. It goes through the first stage, right? First stage uses fuel. The thing is already at high velocity. It's continuing to accelerate, and then what happens? The first stage falls away. The second stage fires, and you get a snap. If you look at the film Apollo 13, they show that very realistically when they're strapped in and they kind of go forward and boom, they're back in their seats there. That's a sudden change in acceleration. That's the jerk. You can see why they call it a jerk. He'll literally jerk backwards, or forwards, depending on your reference, but you literally jerked in a motion there. That's what jerk is. So now think of it. They're saying that there is a sudden change in the acceleration of the liquid iron. Really kind of interesting. So this is a kind of a fascinating find here about that there's weird things going on. You get these blobs of molten iron, and it affects localized effects on the magnetic field. Interesting. Goes to show you there's a lot to this planet we still do not yet understand and know about. Thank you for your time. Hey folks, just a reminder to please share my videos with others, and to also please tell others of my channel. Please subscribe, and don't forget to hit the bell so that you receive notifications when I upload new videos. I also hope that you will consider supporting the work that I do and supporting this channel by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.